Evening all. I'm happy to speak here. Hyderabad is a place where I learnt everything about politics, everything about critical thinking. And I'm a student of University of Hyderabad. I did my PhD there. Professor Tandon is my advisor who is here. I'm very honored to have him also here. I was at ISI for some time as a PhD student, and later I also was there as a postdoc and also at HRI. But essentially, I moved out of mainstream mathematics and started looking at education. When I moved to education, I didn't think there was anything actually. I thought I know all the mathematics. I just need to go and teach. That's about all that I knew about education. But Eklavya, with its solid work in education for several years, decades actually, that provided an excellent opportunity for me to actually look at critical things. Eklavya library is one of the best actually. And so, well, I got to, I think also that around this time, around the time actually, my voice is actually pretty loud. Around that time, we also could actually access a lot of literature online now. You know, that is one of the best things, you know, that to be able to access literature, to be able to read. And I also had the opportunity to visit several places. And so all these actually contributed to looking at mathematics critically, which is something that I could not do as a student of mathematics. As students of mathematics, we are not exposed to anything beyond just doing mathematics. We do not know the history of mathematics. There's not a single course on history of mathematics. We do not ask anything critical. We don't even look at, say, pedagogic issues. That's something that might be of value for a learner who might eventually, after a postgraduate degree in mathematics, one may become a school teacher. So some of the pedagogic issues, at least one could be kind of exposed to. None of those things happen actually. That's also one reason why I think this talk actually means a lot to me. So for most of us, our notions about mathematics have been acquired from our experience of mathematics that we learnt at school and popular notions about mathematics that is promoted by media. Media actually does a big job of actually promoting certain notions about mathematics which we don't realize. In everyday terms, these amount to the belief that in mathematics there is one correct way to answer any question, no matter where and when the question comes up, where and when the question comes up, and no matter who tries to find the answer. As long as one uses the correct method, then one will get the same answer. In other words, even though we may not use such terminologies, we believe that mathematics is objective, value neutral, and universal. Perhaps we also believe that mathematics is out there, independent of us. Every now and then, we come across popular articles that talk about mathematics in nature. We also have heard it said that mathematics is the language of nature, or that laws of nature are coded in mathematics. Next slide. Aren't there good reasons to believe so? There seems to be a mathematical order to the natural phenomenon. We are able to describe and predict the motions of celestial objects using mathematics and several things, right? And we seem to have been able to harness mathematics and put it to the benefit of humanity. Mathematics has played a significant role in the development of modern science, particularly physics, but also, I hope you are able to hear me. Yeah, but also other branches of science, even if it is to a limited extent. By now, knowledge of mathematics is considered necessary not only for mathematics and engineering, but all branches of sciences, and even for some areas in social sciences. In this one, one is talking about the formatting power of mathematics, that now we are living in a society where almost everything is already kind of prefabricated. So we are living in structures that are already fabricated, say whether it is, say for example, your finance model or whatever else. I mean, they are all fabricated, prefabricated, and then therefore at the back of all that is mathematics. Therefore, in some sense, mathematics has the formatting power. Given these, it is not surprising that mathematics is a compulsory subject in school. I mean, not just now, for a long time we have had mathematics as a compulsory subject, and mathematics for all is the mantra that state education departments and math education educators chant. National curriculum frameworks declares all children can learn mathematics and all children should learn mathematics. But in the next breath, the national curriculum framework also talks about the need to nurture the talented minority. That seems to be a kind of a given, that talented people, talented in mathematics are going to be a minority is given. Minority, we have heard mathematicians say that the ability to do mathematics is inherent in a person, meaning that if you don't have it in you, then you can't really do mathematics no matter how hard you try. Giftedness is actually a domain of research in mathematics education. Even though there are, I mean, in spite of the fact that there are several, a lot of challenges to kind of received notion of mathematics one finds within math education, the notion of giftedness still exists there in a very different fashion, and it is researched on. Perceived as esoteric, the pursuit of which for a mathematician is synonymous with the pursuit of truth and is timeless and of mystical beauty, mathematics then has all the ingredients that places it beyond the reach of all. Moreover, it allows for priority battles about who discovered which mathematical truth first and contributes to boosting fragile national pride. That's what is actually right now happening. The new curriculum framework that's come up, full of statements about Indian achievement. In the National Education Policy 2020 states a rootedness and a pride in India and its rich, diverse, ancient and modern culture and knowledge systems and traditions should definitely find a place in the curriculum that they'll come up with. And it says that ancient India made seminal contributions to several domains of knowledge, including mathematics. In all this, it would appear we all have a shared understanding about what mathematics is, though that is far from true. We all think that we all have the same. When we are talking about mathematics, we all actually talk about the same thing. The fact is that when we, at a school level, we learn largely algorithms. I mean, we really do not learn. I mean, as a person who studies mathematics, algorithms are not all of mathematics, one would say. We learn a lot of algorithms and formula, factorizing polynomials, finding square roots, solving equations, maybe some puzzles and things like that, theorems and proving some theorems in geometry. But those who pursue mathematics beyond school may have a different notion about what mathematics is. They know mathematical statements have to be proved and learn that there is an axiomatic foundation. That's something that probably one goes to masters, one might probably get to know that there is an axiomatic foundation for geometry at least that they learnt in school. Now, the geometry that they learnt in school has an axiomatic framework, and that there are other geometries also. So these are kind of, therefore, now your understanding of mathematics as a student of mathematics is not really the same as the notion that you have as a person who didn't pursue mathematics. Mathematician exposed to the foundations of modern Western mathematics would concede to the fact that mathematical truths are not absolute, which is something that general public actually believes mathematical truths are absolute, but mathematicians are exposed to the foundations, which is again a rarity. Most of the time we don't get exposed to the foundations of mathematics. Would concede that mathematical truths are not absolute. They are subject to a chosen axiomatic framework, and there is no escape from making a choice of an axiomatic framework. This is somewhat akin to a paradigm choice that is to be made in science. So far I think I have basically said that. I've said that even within the community of mathematicians, the notion that mathematical truth is absolute is not tenable. I mean, they themselves do not believe that mathematical truth is absolute. It is actually, so if you work with a certain axiomatic framework, something becomes true. So later on, if there is a need, I may give an example, but I think that's generally, not probably understandable beyond, it's very much within mathematics that one understands it. So disciplinary knowledge has been and continues to be subjected to critical inquiry, often from those who have been excluded from pursuing it. So feminist critique of, when I was a student here, I heard about feminist critique of history, feminist critique of economics, feminist critique of so many other things, because I was actually learning feminism at that point of time. And feminist critique of science certainly is another thing that, I've really read also. But there wasn't so much about mathematics. One didn't really come across feminist critique of math. There's a little bit, not really much. Challenge to dominant notions about mathematics comes from actually education. This is understandable because mathematics, which is a compulsory subject in school, has the dubious reputation of being a gatekeeper for those who come from socio-cultural and economic margins most of the time. So, mathematics is what, you are somehow memorizing stuff. You can memorize all of physics, you can memorize all of history and geography, even English maybe, and write the exam, and you might just pass and hope to get a job as a peon maybe. But then mathematics functions as a gatekeeper, that you actually cannot pass in math. Therefore, this is not only the story of India, this is a story all over, that people from socio-cultural margins actually get left behind. And they go back to doing what their families come from, and so they cannot really make it to a higher degree or something like that because they fail in mathematics. So educational theories of learning started moving away from behaviorism. Mathematics seems to be one area which is tailor-made for behaviorists. You know, you just kind of drill and practice, drill and practice, drill and practice. Well, I'm reducing, presenting behaviorism in a very reductive way, but still, drill and practice is central to behaviorist approach to teaching something, and mathematics is an ideal candidate for that. But then this approach actually goes for a change, and people talk about learning meaningfully. Meaning making becomes a central thing in learning. So how do we make children learn something, and to be able to learn something not mechanically? If behaviorism would allow you to do things mechanically, I mean, like, you know, reward and punishment. If you know how to do column operations, you know, if you put set of numbers and you can just do column operations. I do not know, when I was a school kid, we had these 3-4 digit numbers, maybe 4 or 5 of them would be lined up, and that one would go column by column, add, right? And absolutely behaviorist. If you do not know how to do it, you will get punished, and then you keep till you get it correct. This goes on. So it ideally suited for behaviorist approaches. But then meaning actually, that learning things meaningfully becomes central, not just mechanically, but meaningfully becomes central. And so people start talking about situated learning. Okay. So the work of people like Jean Love and Wenger, cognition in practice, situated learning, legitimate peripheral property. They actually talk about learning by doing something, learning mathematics also in the context of doing something, and that meaningful action, these become central. So then actually one is able to look at why actually children are not able to learn mathematics. It's very, as anybody who has actually tried working with children will find that you may actually teach them a certain algorithm. Like, I remember this experience that I was in a classroom. The headmistress, who was also a math teacher, she came and she explained to the class, 7th class children, very patiently, why 505 divided by 5 is not 11, 101. She actually worked out the whole thing. Then they did 606 by 6, 707 by 7, 808 by, all correct. 1 month later, 505 by 5 became once again 11. That's because, but if you ask them, if I give you 505 rupees and you share it amongst 5 people, how much would each one get? They never commit a mistake there. They never commit a mistake there. So what's happening? The algorithms are blind. You do the algorithms not knowing why you're doing the algorithms. When we teach children algorithms are black boxes. We don't actually explain why the algorithm works. We simply give the algorithm. Most of us do not know why, for example, the square root algorithm works. All of us are good, adept at it. I mean, division algorithm itself is something that we do not know, right? So, so this is one of the major difficulty that we face. Next slide, please. So by the 1960s, mathematics education researchers, in their attempt to situate learning of mathematics in context meaningful to the learners, took note of different forms of mathematical knowledge that existed outside what was taught in the schools. So what are the other forms of mathematical knowledge that exist? Indigenous mathematics knowledge, referring to mathematical practices of certain indigenous communities, which is obviously something that they did not learn from school because they have not gone to school also. Informal mathematics, referring to everyday mathematics, which is different from the formal mathematics taught in school. Oral mathematics, prevalent among all societies and passed on orally from one generation to the next. Street mathematics, referring to the mathematical knowledge of street vendors and so on. All these, we have had all of this. We have had in India also, fraction tables. At one point of time, people used to remember the fraction table. So oral knowledge, mathematical knowledge, they are illiterate maybe, but they have mathematical knowledge. Knowledge that is, knowledge and memory. So there's this very beautiful book by Sendil Babu, which actually talks about how memory itself is a very different kind of, it's not rote learning that we had here. He calls it a reconstructive memory. So that kind of a memory was always part of this oral traditions that existed here. I'll also share one experience. There was once I was making children think of a number, double it, add it to itself and tell me what you get. So basically, if you think of x, then it is double it, 2x, 2x plus 2x, you are supposed to tell me 4x. I was trying to get them, this is class 6 students, algebra is part of their curriculum. They were, I mean, I really did not know, I was just experimenting like this. So many children came up with different numbers. So I thought that, okay, various people would, finally I would be able to say that, okay, now x is a variable kind of a stuff. So somebody said 40, then I asked what number did you think of, 10, somebody said 100, what number did you think of, 25, it just went on like that. One student said 10. This was an absolutely uncommon number. So I said, what number did you think of? It was in Madhya Pradesh. So he said, die is 2.5. Now, die when you double it, it becomes 5, 5 plus 5 is 10, that he knows, he got it correct. But then how did he think of die? Now I bet that he couldn't write die, 2.5, he wouldn't have been able to write 2.5. He comes from a milk when selling family. He goes with his parents and sells milk. And he knows that 2.5 liters of milk, when you double it, it's 5. And so this is an example of knowledge that is actually mathematical knowledge that is embedded in practice that children sometimes bring to classroom, which unless we acknowledge, we wouldn't even know how to tap it and use it in the classroom. So, this approach is looking at people's mathematical knowledge actually. Several people did very exemplary work. Gay and Cole's work with Pele traders, I don't know how to pronounce the name, unschooled Pele traders in Liberia. Their ability to estimate quantities of rice was supposedly better than the educated Americans. That's what they found. I mean, of course, they found much more than that. Just this is one example. Teresina Nunes' work is really very remarkable. She actually was trained psychologist. And when she was in Brazil, she was sent a whole lot of children saying that they have learning difficulty. So she actually worked with them and found that they had no learning difficulty at all. She found that they're all perfect, they have no problem. Then actually she moves into trying to understand what is happening in school, what is the kind of mathematics we are teaching in school, and what is the kind of mathematics these children have. All these children that she worked with, she was referred to, they were all vendors. They actually stood on the street, and when you buy something, they can do all the oral computations and take money from you, give the balance, no problem, absolutely perfect. But the same problem when you give them in the school, the same problem they cannot. So another motivation for researching mathematics outside the modern Western canon came from the demand for culturally focused courses from black students as part of the alternative affirmative action movement in the US in the 1960s. Claudia Zaslavsky studied and documented mathematical knowledge such as complex geometry and patterns embedded in the artifacts of African culture. She was a math teacher in the US who realized the importance of incorporating mathematics from African culture in the mathematics curriculum for her students to have pride in their cultural heritage. And this is actually a thing that we have to, I think, come to at some level, because I mean, we are talking about pride here, and we are also, this whole country is also at this point of time talking about national pride, and I think there's a little discussion that we need to have here. The work of Zaslavsky and Paulus Gerdes brought to light rich mathematical knowledge found in African countries. So she's Zaslavsky. She goes to Africa because her son gets a job there. She goes there with him, and then she actually goes around and finds that there's so much knowledge that is that's there hidden. So there's this book by her called Africa Counts, the Socio-Mathematics of Africa. The dedication says to those Africans who are now engaged in the formidable task of reclaiming their heritage, and ends with scholars including educators must accept this challenge to continue the work of reclaiming the rich mathematical heritage of Africa. The book is divided into 8 sections. Section 2 is titled Numbers, Words, Gestures and Significance. Section 3, Numbers in Daily Life. Section 4, Mathematical Recreation. Section 5, Patterns and Shape, and so on and so forth. It's a very nice book. I have not had the opportunity to actually go through that. I have just looked at it because, I mean, it's not available here. So some of the things that you see here, I mean, that kind of constructions that are there, this basketry from African countries. I mean, Paulus Gerdes has actually published a lot, enormous lot. So I just took 2 examples of his books, Geometry from Africa, Mathematical and Educational Explorations, and this other book, Geometrical Recreations of Africa. Then there is another person, the Ashers, both of them, Marcia Asher and Robert Asher. Robert Asher is an anthropologist and Marcia was a mathematician. They both wanted to do something they wanted to do something together. So one is an anthropologist, another a mathematician. They wanted to do some work together. Therefore, they actually went and researched the mathematics of the Incas. So then she has a book called Mathematics of Incas, the Code of Kipu, where basically, I mean, she says that when she went and she actually looked at this tool, she just didn't know what it was. And so she was approaching it from a mathematical point of view, trying to understand what could it be and what, I mean, reading and making sense of it, and whereas her husband actually was looking at it from anthropological perspective. So then actually that, so this particular tool, this was used, you know, it's a lot of threads. So they used to use it both as a recorder of, so you could actually store the number and also use it for computations apparently. That's the kind of knowledge that's lost. So she also did, after that I think she continued her work with, anthropological work with mathematics, and so she also looked at Angolan mathematical knowledge. So she has this thing called Angolan sand drawings. You know, I actually saw this Angolan sand drawings here in Hyderabad sometime around 2000. There was a couple here, Steve and Janaki. They ran a school, Anand Bharti I think was the name of the school. She actually showed me these Angolan sand drawings when for the first time I saw it here. So of course, I mean, what we see here are not strange for any of us, because we have seen similar things in India. You see this column, I grew up doing these kind of columns, when I was young. It was a competition, we all used to, the month of Margari was a month when we really would go on with this thing. Very complicated ones, and that was a challenge. Sometimes, this knotted one, simply the whole column may consist of simply one thread. It's the most difficult one to do and most challenging one to do. So it was quite fun to do these kind of things. And I mean, one realizes that there is some kind of an arithmetic series there. You can actually make smaller ones and then you can keep making bigger and bigger ones. Same thing with this Hriday Kamalam column also. And of course, basketry. And carpet weaving. Carpet weaving, there's a person who actually studied the Kashmiri carpet weaving work. She did some work, Kaur. So this, then Sendil Babu, of course, who's actually looking at mathematics and society. So the knowledge of mathematics that is embedded, that's not the Bhatta Bhaskara tradition of mathematics, but people's knowledge of mathematics that is alive. In the sense that Bhatta Bhaskara tradition is in some sense dead. This is still there. So he's trying and documenting these, and so I just took this from his book. This one where a woman is weaving, you can see patterns there coming. So what is the mathematics embedded there? None of us actually have studied. And also boat building. Boat building, boats cannot really survive on the fire. There is, the person may not be able to write an equation, but then the boat can go. That means that there is a certain amount of mathematical knowledge that's embedded there. So these are some things that we know. So okay, so then yes, people have some mathematical knowledge. So what about it? So why talk about what is ethnomathematics? Okay. So the thing is that whatever I said about people's knowledge so far, if you say, okay, now I start with basket weavers mathematics or street mathematics, can I eventually go to solving Fermat's last theorem or prove something in mathematics? Of course not. That's not the idea also. So, but then one thing one should note is that we are setting up a certain mathematics as a kind of a measure against which every other form of mathematical knowledge has to actually prove its worth. Reducing mathematics simply to the product, the mathematical truths. Say for example, every number can be written as a sum of 4 squares, or that the equation x squared plus x to the n plus y to the n is equal to z to the n does not have non-trivial integer solutions for n greater than 2 and things like that. If that's all that one is talking about, then one says, okay, no, we did this before you did, and so on and so forth, right? But then this actually leaves out the context in which mathematics emerges and enables that form of mathematics which has a power at a certain point of time. And we should not think that only what we are the mathematics that we are doing in the universities today alone has power. At different points of time in history, different kinds of mathematics had power. So that form of mathematics which has the power at a certain point of time to validate or reject and subsume others as inferior versions of it. So why learn people's mathematics? It's all already there in what we are learning in teaching in school. At present, this power lies with what is referred to as academic mathematics, namely the mathematics pursued in universities across the world today. This form of mathematics, seen as Eurocentric and white supremacist by some, definitely, displaced all other dominant forms of mathematics across the world and situated itself at the center. For example, ancient Indian tradition of classical mathematics, the Bhatta Bhaskara tradition of mathematics, is not anymore alive. Nobody does it. We all talk only about the history of Indian mathematics, the greatness of the past. We are not able to continue. Like, for example, I cannot say do one course in algebraic geometry and another course in something else that was done in India. They do not sit together. They are very different. They are not the same. Right? It's doubtful that Chinese and other dominant traditions in mathematics manage to survive and coexist alongside academic mathematics. So we will use we in math education now use the term academic mathematics to refer to the mathematics that is practiced in the universities, and indicating that there are other forms of mathematics. Okay, so then Ubiratan D'Ambrosio is considered the father of ethnomathematics. He actually said, I heard him first in 2008, he says that, why is it that forever we are catching up? They are always going ahead. We are always trying to keep pace with them. We are never able to get there. Right? They are always showing us the way. So Eurocentrism in mathematics was a problem that actually he actually talks about. And then he says that, he coins the term ethnomathematics in 1977. He says his early ideas of ethnomathematics came when he joined UNESCO in a project for a graduate center in Mali. He is a Brazilian mathematician. The center, this is the Center for Pedagogic Superior, whatever, I can't really read these things, in 1970. There he met frontier research in such areas as architecture, religion, history, language, environmental studies, and of course the natural sciences and mathematics. So there, for the first time, he actually also sees that they are talking about ethnic knowledge. So he also thinks, okay, now how do I look at mathematics also from this perspective? Okay, seen from the perspective of the discipline of mathematics as practiced in universities, the forms of mathematical knowledge I described earlier, and including what one will call as ethnomathematics, they seem very primitive. They seem primitive forms of mathematics. But according to Ubiratan D'Ambrosio, this is because the role of culture in knowledge construction has not been inquired into. In his 85 paper, Ethnomathematics and its place in the history and pedagogy of mathematics, Ubiratan seeks to redefine mathematics in such a way that the role of culture becomes evident in the creation of mathematical knowledge, and different forms of ethnomathematical knowledge could claim equal status as forms of mathematical knowledge. Universality of mathematics cannot be sustained. Research shows evidence of practices which are typically mathematical, such as counting, ordering, sorting, measuring, weighing, done in radically different ways than those which are commonly taught in school system. So then, he defines ethnomathematics. I want to actually, even though he begins with mathematics, mathematical knowledge of tribal communities and ethnic communities and all, he actually does not stay with that definition. He expands it and he actually radically revises it, and it's really one of the most wonderful things that he did. He says that in contrast to the academic mathematics, we will call ethnomathematics the mathematics which is practiced among identifiable cultural groups. Now, what are the cultural groups for him? Such as national tribal societies, labor groups, children of a certain age bracket. For him, that's a cultural group, professional classes, and so on. Ethno means a culturally identified group sharing jargons, code, knowledge and practices, language, symbols, myths, and specific ways of reasoning and inferring. This includes practices such as ciphering and counting, measuring, classifying, ordering, inferring, modeling, and so on under ethnomathematical practices. Now, he has this breakup of ethnomathematics as follows. So, he breaks it up into three different bits: ethno, mathematics. Techne stands for ways arts, techniques, that one uses that term, TICS. Mathema for understanding, explaining and learning, and ethno for a group within some natural or socio-cultural environment that has a compatible behavior. Okay, so for him, so for example, he would actually say that physicists or engineers, the mathematical knowledge that they have is also ethnomathematics. So it's not only, so because it's not often that mathematicians approach to mathematics, the reason for which mathematician does mathematics and the reason for which, say, physicists approach mathematics or engineers approach mathematics are not the same. And therefore, they cannot really work for long together. They may they may overhear each other, they may kind of keep track of what the other person is doing, but they actually function among themselves. They actually, they might, I mean, as a student of mathematics, I know that, the symbols that we use also may be very different, and so on and so forth. Here are my friends who might actually agree or disagree with me soon. Yeah, so he would talk about them as also, their mathematical knowledge also as ethnomathematical knowledge. School children's mathematical knowledge is also in some sense an ethnomathematical knowledge, because, say for example, when you are in school, you know that some of the internal angles of a triangle is 180. You do not know that some of the internal angles of a triangle is 180 only because that's what has been told to you. You measure and it doesn't ever add to 180, it will come to 179 maybe, sometimes 181 maybe, then you say that, oh, my pencil is not sharp, you sharpen it, try to do it. You don't really realize when you are in school that this is not an empirical truth. The sum of the internal angles of a triangle is actually two right angles, is not an empirical truth, it's a logical truth. It is deduced from the axioms of mathematics. If you try to kind of bring the logical truth, if you want to check the logical truth by empirical means, you are not going to get there. Empirically, if you want to talk, you can only say this much, that some of the internal angles is kind of maybe around 180. Because, measurement can never be exact. Measurement is dependent on that tools that you use for measuring, right? Mathematics is exact. Mathematical truths, they want it to be exact actually, right? That's why it is actually put in an axiomatic framework. At least in a certain domain. Indian mathematics was not axiomatic. In India, mathematics was, Indian geometry is not axiomatic. Greek geometry was axiomatic. So it was not that all across the world, everybody thought of axiomatic framework naturally. It happened in one place. Then it later becomes also the framework for all of mathematics in the 19th and 20th century. Work in foundations of mathematics actually is to, 17th and 18th century mathematics, where actually calculus develops. At that point of time, they kind of take a break from this obsession with rigor. That, I mean, as my friend Ambar Habib actually argues in his paper, that allows them the freedom to create things actually. And it is later, by the 19th and 20th century, that foundations become very important and all of mathematics is put back again in an axiomatic framework. Hilbert's program, to attempt to actually give a very concrete foundation to mathematics comes into, it's called the Hilbert's program. Well, now for now things have changed. Axioms are not anymore self-evident. When actually Greeks started with axioms were seen as self-evident truth. So there is no need to prove the axioms. Rest, you assume the axioms and everything else use deductive logic and established. Therefore, in some sense, mathematics was fine. But by 20th century, we understand that, there's nothing self-evident about it. And so we take the axioms, they are formally axioms. We take a set of statements as axioms, which will not contradict everything that we know mathematically so far. But then, so Hilbert's idea was that we somehow will be able to arrive at a finite set of axioms, and with that now, given any mathematical statement, you can either prove it or disprove it. That was his dream. But that actually gets a beating when Gödel actually shows that in every axiomatic setup, sufficiently qualified, say for example, it should actually have the set of natural numbers in it, there will always be statements which you can neither prove nor disprove. So then you have to now decide what to do with this statement, whether to accept it and take it. You have to only, it becomes, therefore then it becomes another axiom. You have to add it as an axiom. Therefore, if you accept the statement, then that is one mathematics with that as an added axiom. The negation of it somebody else could take. But I mean, that doesn't happen. We work within a certain, that's why I said that, in a certain sense in which paradigm choice also, when Kuhn talks about the paradigm choice, there are competing paradigms available for you when actually, when you want to change from one paradigm. Which paradigm which we will choose depends on, not really logically, but it depends on power and other prestige and such things. It's the factors that are outside science. Similarly also, the choice of axioms is definitely done by certain people who know enough mathematics, who are considered the right people to make those choices, and then the rest of us simply function within those choices. We do not have several mathematics operating at any point of time. So one should not really think also that if it is not, see, mathematicians say that, we do not do mathematics because it is useful. One of the things that we all learned when we were in university was that we do mathematics not because it is useful, we do mathematics because it is beautiful. It is the beauty of mathematics that appeals to us. It is a pursuit of truth. We don't care whether it is useful or not. Fermat's last theorem has been proved in 1993, it was proved. It doesn't make a difference to anybody. Whether a number can be written as a sum of 4 squares or not doesn't make a difference to anybody. But then except mathematicians. For them, it could be a life and death question. Fermat's last theorem actually was a life and death question for a whole lot of young men who actually said that what is the point in my life if I cannot even solve Fermat's last theorem? And it can actually mean that much. So, but then, so when we talk about ethnomathematics, then is it all utilitarian in nature? And so here is this wonderful dialogue between Ubirathan D'Ambrosio and Marcia Asher. I just want to, this is just a part that I took out. Asher says, survival, yes, problem solving, yes, but something more, something that transcends the immediate. Culture plays a significant role here. That is how one understands actually culture there. Ubirathan says, if you really want to solve the problem of trisection of an angle, which is again one of the very well-known problems, trisecting, and is it possible to trisect an angle using only compass and a ruler? Ruler and the compass is not the ruler and the compass that we actually can hold on in our hand. These are ideas. The ruler and the compass is not a material thing, they are actually ideas. Because nothing in this world can be really perfect, that nothing can actually, you cannot really put a point or a line, nothing can be done. You have to only do all of them in words. And so if you really go on, now it's available for us to read all the 13 volumes of Euclid's 13 volumes. The first volume has these definitions. If you really look at the definition, if you actually try to understand the definition, understand what a straight line is by reading the definition of straight line given in Euclid, you'll never know what a straight line is. So, they were compelled to refine things and put it in such a way in words so that logically they will not arrive at a contradiction. That whole exercise is absolutely fascinating at one level. But at the same time, that's also only one approach that one should see. Okay, Ubirathan says that so the thing of trisection of an angle, you can say you can easily do it, as many people did. But the moment you limit yourself to the use of ruler and compass, you are at another level of reflection, trying to go beyond to transcend the immediate needs. This is the same for several cultures that have ritual geometries also. Asher says many mathematical ideas are totally unnecessary. By unnecessary, I mean that we do not need beautifully patterned mosaic on the floor in order to walk on it. It doesn't make walking any easier, but people put in a great deal of effort to create those beautiful floor mosaics. So Ubirathan says every culture tries to reach above the mere earthly needs of survival. We have found in every culture these kinds of intellectual exercises, these plays and these games as practices that allow people to approach the considerations that go beyond pure survival. I thought it is very important to say this because we might actually simply think that it's only utilitarian form. Ethnomathematics is all about only utilitarian mathematics. That's not the case. Okay, so in response to, again, these are all things that I'm quoting from Ubirathan's work. In response to their own environment, such as environment, each culture has developed its own system of knowledge which uses a different way of observing, comparing, classifying, evaluating, quantifying and measuring, counting, representing and inferring. All of these different knowledge systems that resulted from an effort to cope with different environments should be called ethnomathematics. They are all motivated by the drive for survival and transcendence and are compatible with their myths, religions and language. Although similar reactions may occur in different natural and cultural environments, each context has its own responses, that is its own ethnomathematics. So it doesn't make sense to say, okay, who proved Pythagoras theorem first? Pythagoras theorem came up in different contexts, maybe for different reasons, in attempting to answer different kind of questions. So to be able to simply ask this question like who proved Pythagoras theorem first, actually is like comparing apples and oranges, is what one would say. Greek geometry, Indian mathematics, the Inca mathematics, mathematics of several cultural groups that exist and continue to continue to practice their form of cultural groups that exist and continue to practice their form of mathematics. Mathematics created or used by engineers, physicists, statisticians, accountants. Accountants have used they create their own mathematics, right? They also have their own symbol system. Accountants, academic mathematics are all ethnomathematics. So there's this book by Seidenberg which actually looks at ritual origins of geometry and ritual origins of counting. So there is an increasing demand for education in every small country, and ethnomathematics can contribute to addressing a number of global challenges school system face. We can, I think, come back to this. Ethnomathematics is more acceptable to native populations and are more accessible and affordable, mainly for those living both in rural and coastal areas. Obiratan says, it appeals to traditional practices, hence it is more attractive than the sometimes cold and austere forms formal mathematics in their existing programs. This is also true in more developed areas where services are a mix of traditional practices for common needs that rely on specialized workers and artisans such as builders, maintenance people in general, as well as on more specifically trained professionals in the areas of universal interest and reach, such as commerce, industry and technical services. This is the basic component of ethnomathematics, which should be an option and a choice offered by a well-functioning school system that balances ethnomathematics and official school mathematics. The two systems need not clash, can blend in harmony. There may be an effective improvement in school mathematics, but also improvements of ethnomathematics, which may receive valuable contributions from theoretical reflections offered by academic mathematics. Not all who study math in school will pursue a career in math or related subjects. People who live in rural locations do not seem to need academic mathematics for their everyday life, though individual children may aspire for a career in math. Can school mathematics meet the needs of mathematical knowledge required for life in rural locations just as it does for life in modern technological society? I think that is my last slide. This is a cautionary note saying all this, because I also actually I browsed, I mean now YouTube has so many videos. If you just say ethnomathematics, you will find a lot of videos on ethnomathematics. And I also looked at ethnomathematics in India. There's quite a bit which is looking at, and I think I saw Vedic mathematics. I didn't read, I just looked at it. So therefore the question about such things as astrology and Vedic mathematics, are they ethnomathematics or not, arises. Ancient Indian mathematics certainly is ethnomathematics, because it functioned in an entirely different context and it had very different kind of purposes for which it was created, and it is not there anymore in that sense of the term. Does ethnomathematics refer to forms of mathematical knowledge that exists now? Yes, it does. Certainly, we need to research and understand the mathematical knowledge that the weavers have. For example, I mean, Mangalagiri, I went and saw the looms, and I can see that there are so many things. But I mean, to be able to work with and understand the kind of mathematics that's embedded in it, I would need a little bit, I mean, I need probably somebody else who can explain also certain things. And and there are several such things, like for example, shoemakers, I mean Kolhapuri shoemakers, they have their, I mean all these people are doing things, I mean they have to do several things which call for use of mathematical knowledge in different ways. So we have to study all of them. We have done no such studies. But then what about astrology and Vedic mathematics? Astrology, I know, uses some mathematics, I think. Can we call them ethnomathematics? My answer is no, for two reasons. For the simple reason that Vedic mathematics, what is referred to as Vedic mathematics, is a book written by, it is a bunch of 16 shortcuts in mathematics written by Shankaracharya in the 20th century, 1950, somewhere between 30 to 50. With the sole aim of trying to promote the greatness of Indian mathematics using this. It is very much within the Western, it does not, has nothing to do with ancient Indian mathematics. It's completely a modern product. This Shankaracharya, I shouldn't refer to a Shankaracharya, somebody may take offense and attack me. This Shankaracharya was actually an MA in mathematics and also an MA in Sanskrit. Very good apparently, very brilliant man. So he sat and did this, and with a very stated mission that he will actually go and take it from village to village and actually talk, that's school level mathematics. Vedic mathematics, things are something that you can actually communicate to anybody. I may not be able to understand ancient Indian mathematics because it's so very different. Even to make sense of it, it might call for much more than what many of us actually know also. But not Vedic mathematics. It's very easy. You can go and show, like, quickly you can do this, quickly you can do that, and then you can say that, Indian mathematics was so great, Indian mathematicians knew everything. You can learn in 1 year all the mathematics that is being taught. You are learning in 23 years in a university, all of that you can learn in just 1 year. These kind of claims were made. I mean, it's all written in the introduction to that book. That book is available anywhere you can buy it. So it is definitely not ethnomathematics. It does not satisfy any of the criterion that, if I follow the definition that Ubirath and D'Ambrosio gives. And same with also astrology, sorry. As far as I understand, though some mathematics may actually be there, I don't see this, I am not able to imagine, I do not know any astrology, but I want to say that. I mean, I can't believe that the mathematics that they needed for astrology was organically developed by them for their use. I think that they actually used certain mathematical knowledge to be able to do some kind of a computations, where of course, yeah, if you all do the same computations, you'll all get the same conclusion. Many of them predicted that Ramanujam will die young, and that all of them looked at his horoscope and predicted the same thing, because they all, I think, used the same algorithm to do that. Okay, are we suggesting then that there's a new thing that's happening in India right now, this Vishwakarma Yojana, the government has come up with. So this allows for young people to go back to do traditional, if a young person after finishing school or whatever, I mean, that I don't think that's required. But if you want a loan to pursue your traditional occupation, that if I come from a weaver's family, if I can get into weaving, if I come from a, some other metallurgy, some, blacksmith, whatever that, if I can continue my traditional occupation, for that the government will give you some loan only. It's not even a free thing. So basically, in some sense, the government is in some sense trying to, Tamil Nadu, there is a lot of resistance to this Vishwakarma Yojana in Tamil Nadu, saying that why are you pushing us back to that which actually refers to our caste. That's one of the biggest complications for us, that traditional occupation is also, caste-based occupation. When I asked actually a weaver in Chirala, we went to a weaver's family, we asked, like, this year they had this thing in the house. So I said, what about your children, will they do this? Their immediate response was like, Endukama, valenduku chestarama. They will not do. Why will our children do this? Because it is not respectable. In a way, you want to escape your caste identity also by saying that you will become an engineer. It's much better to pay those lakhs and get a degree from and become an engineer. That washes off a certain amount of your caste also at some level maybe. So, it's a very complicated question for us. So, definitely nobody here, and I think there's a lot of anxiety in India about promoting ethnomathematics, because there is this fear that, okay, if you introduce ethnomathematics, then it will be only given to those who are coming from the margins, and therefore we are talking about differentiated curriculum and so on and so forth. Those are very valid concerns, and we really need to be wary of them. But that doesn't mean that we should not really look at the mathematical knowledge that people have, because that's also that, when I look at a child, then I can actually think of this child as coming from a home where there is a certain practice, there's a certain kind of mathematical knowledge that the child may have, and that the school mathematics should somehow speak to it. That is what I think one should do. There I end. Thank you.
Professor, that's really a very fascinating talk. You covered much more than what was in the article published in the India Forum. Not to plug the article, but those who would like to go back and reflect on this, she wrote an article about a month or so ago in the India Forum on ethnomathematics. I would strongly recommend that for understanding. Now, if there are questions that
I have a few questions. One is that you didn't deal with the cultural trends of the mathematics of music. And I would like to know why, you think that it's not a cultural trait?
No, of course it is. I mean, that is one of the many. I think in some sense, this often talked about mathematics and music is very well, I think acknowledged in India also. Well, it's just that, I didn't really, I personally myself, I cannot sing, I do not know music, so I don't, that could be the reason.
Because I think that there are very complex mathematics in the rhythm.
See, one thing, there are lots of issues also around that. One is that mathematical knowledge, Indian mathematicians believe, constantly we have been told that, not all Srinivas Ramanujam could do it, and then a few others could do it, not everybody can do mathematics, it's inherent, it's born with it. Music is also something that you're born with, But basket weaving or other things, is not something, nobody ever talks about, you're born with this inherent ability to do basket weaving.
Okay, if you're something with born with, then I have my next question on this. Is there something called a gene for mathematics?
I'm not qualified to answer that question. I don't think that there is any. When if the whole argument is trying to say that almost every culture has actually had its own form of mathematical knowledge. So how could one identify a gene for mathematics? Biologists might be able to answer. I do not know how to answer that.
No, because considering that you find that let's say the blacks, there seems to be something in their genetic structure which makes them very good sprinters and long distance runners. Is there something like that which, is there any body of work on that?
There could be actually. The thing is that in a way, I may not really be focusing on such things because I also tend to resist them, women are supposed to not be good at math, there's so much like is math, a male domain was actually an area of research. For about 20-30 years, there was serious research in US schools trying to understand, are boys naturally better at mathematics, are girls naturally not so good at mathematics? Now, this kind of fixing it to gender or gene or something like that, for me it doesn't seem like, I don't see it as productive.
Okay. I just have two more questions before. Sorry. One, mathematics of time. Of time.
Okay, time.
Yeah. When we say that one of the basis of time in the relativity theory is that it is not a constant and there's some huge level of abstraction in that concept. This is my theory which I just developed in the last 10 minutes. People who meditate, we always say that they meditated for 10,000 years and then come back to find their wife only 6 months older. So there is a concept of relativity of time, and that's a level of abstraction. Do you think that some cultures are capable of a higher level of abstraction than others? What in your large work?
I'm not aware of it. One thing that one can say is that when it comes to measuring, measuring time is not a very easy thing. How do you measure time? You need to really, you have to devise. Length measurement is not all that difficult. You could actually use, there are tools on your body you can use. Even area you can measure.
Yeah.
Weight measurement already becomes not so very easy. You need to have, it's an indirect form of measurement that you'll have to do. Time measurement is, that it can be measured and that you'll have to, is quite a, I think, it's an interesting question. In measurement, when we teach measurement in school.
I think there are societal systems which actually pushes ethnomathematics out. For example, in India, we had this taka ana pai. Okay, 16 annas make a taka and so on.
Yeah.
Similarly, sher, chotak, mon. Now, I have seen kirana shops or vegetable walas use those numbers so naturally. They haven't gone to school or anything, but we just tell them 1.5 share and 2.5 rupee per kilo, per share, They will compute and tell you, oh, this is the amount that you have to give. Now that has got totally replaced by
Metric system.
getting into the metric system.
Universally. Across the world. Across the world this has happened.
Exactly.
Yeah.
So I am saying now, should we look at ethnomathematics differently?
Of course. I mean, somebody like Senthil Babu does it in his book, Mathematics in India. He actually does that. And not only that, you know, it's very base 10 as we take it now. We take most of the time. Of course, now also we use 60 as a number base when we are looking at time. But, you know, earlier on, number base was not always 10. It was either 12 or 16 or 60. These numbers had many divisors. And, you know, along with all those things that you mentioned, there are also these different number bases that were there and the tables that went with them. All of that, all forms of those knowledge are kind of now, we can only document them. They are not there anymore in everyday use, and almost everybody is using the metric system.
Isn't that also the practical use
Of course, of course, yes.
the whole number theory itself?
Yeah.
Societal response.
Right, it is a, I mean, right now this whole adopting the metric system is like a, you know, form of globalization that has really led to it, but we still might in some places use other things, but currency is gone, yeah. Yeah, it is, I mean, it's a loss, it is a certain, it's a loss of a certain cultural form of doing mathematics, yeah.
I am myself a student of mathematics. I had my MA degree in mathematics and statistics. What we learnt in our younger days, in those days, is very different from what it is today. I say it from my grandson, for instance, how he solves the problems, what I used to do in my clinic times. The point, I will make some 2-3 points only, very teasing questions. One question is, there is a French saying, one mathematician more, one human less.
Okay.
Of course, I should not agree to that because I myself a student of mathematics. The point here is, mathematics people generally are very serious, look at the sky like this, they are very attentive only to their subject, they look nothing else. Even if a lion goes up past, they will not bother about it because mathematics is so attractive for them. Very good, that's kind of an intensive mathematics. But why is it in the society, mathematics is a kind of enemy? The reason is, as you said very correctly, if it's history, geography or English, you can write 3 pages, 4 pages, 2 pages, then get some marks and pass. But mathematics, if you don't solve it, you are done with. That's a problem. So there is a need for doing creative work, which sometimes expels people. They don't want to do it. But has it improved in the last 50, 60 years of your experience is one question. Mathematical tools, particularly, to various occupations, etc., culturally oriented and so on and so forth. But as far as non-ethnic mathematics is concerned, I didn't catch what exactly are the examples. I don't even quite, I didn't quite understand that. You could kindly examine. Even ethnomathematics, you can make it in your own way. Whether I am understanding it as applying mathematical tools
no,
for,
I mean,
for
that's
basket
not,
weaving or weaving or kinds of things.
No, that's not what one is saying at all. One is saying basically that they did not learn mathematics from somewhere and applied it here. The actual context in which they work, the mathematics that was needed for them, in the form in which it was needed, was created by the communities that actually engage with that work. So this mathematics is not learnt from somewhere. It's not that they are applying mathematics. They are creating mathematics. They are creators. There are different mathematical knowledge forms that exist across the world created by people who are actually in the practice of something. That mathematics they did not learn. I mean, like it's not that a weaver learned from a carpenter or a carpenter learned from somebody else or everybody went to a school and learned. Not necessarily. They actually evolved it. So that is the thing that the knowledge actually is a community product. The knowledge, that mathematical knowledge actually came up in that context. That is the whole point that one was trying to make. And also with same thing, also with, say for example, Ubinathan Ambrosio gives the example of Dirac delta function, and he says that, I mean, sorry for those who are not technical term, Dirac delta function, he says that, it is not a function actually, it is a distribution, and that the difficulty was in trying to have this thing that takes value 1 at one point, but then its integration actually comes to, by this thing, integration should be 0. Integral should be 0, but then it is not 0. Now, how to, the physicists needed it. Mathematicians did not have the tool to provide it. And what he says is that first physicists went ahead, and then mathematicians created the mathematics needed to actually legitimize it. And therefore, in some sense, physicists are also creating mathematics. Engineers are also creating mathematics because they try. I teach mathematics for engineers. I teach a lot of linear algebra, whatever, discrete mathematical structures, etc. They don't understand most of it. But when they actually need it, they are going to understand it very differently. They are going to learn it from there, in the context of application. They are going to probably use more or less the same words and symbols, maybe sometimes not, but some other way of learning, which I don't know. When I go to teach mathematics, linear algebra for engineers, I do not know how the engineers want this linear algebra, how to actually look at it. I don't know. I know it the mathematician's way. I teach that only. Changed, meaning like it's progressed, no? See, the axiomatic framework is fixed. So what we call as academic mathematics, I don't think that has changed. It has progressed. Even a lot of new mathematical knowledge has been produced. Yeah, this is a question like applies to all traditional forms of this thing. Which I mean, when India and say Brazil are countries where still traditional knowledge forms are in use, everyday use. I mean, weavers are still weaving, and bullock carts are still there, and people are making them, and therefore, in some sense, these knowledge forms still continue to exist.
You know, your dhai wala example stuck, and then your observation on Pythagoras, right? It's not as if it was handed down from the mountain on tablets. People organically arrived at the same. But I think the key difference for me that I'm not able to, is that there is an aspect of generalization, right? You could be using Pythagoras without actually understanding, or Euler's equation without really knowing that it's Euler. So I think, where does that line?
No, one can definitely, I mean, see, that's what, we are not doing mathematics only because it is useful. We have questions like, can I trisect an angle using only a ruler and a compass? That question does not serve any immediate purpose. I mean, you just need, if you really need to trisect an angle, just go ahead and do it and get on with it. But that's not what one wants to do. They want to actually answer this question, can I do it? Using only, now this obsession is a legitimate obsession. One is not critiquing it. One is not saying that one shouldn't do it. But one is only saying that only that doesn't become mathematics. There are also other ways of doing, just as this is your obsession, there are also other kind of contexts, other kind of obsessions that other people have had in their context, and we need to really look at their myths. I mean, I really appreciate the use of the term myths over there, that that you have a myth that their mathematical truth exists, that length of this object has a definite length, is a certain notion that we have. I really cannot, for example, know it. I can only have the notion. I cannot really measure its length. All of us cannot measure its length once and forever exactly and say that yes, this is the length of this object. This object has a length is an assumption that I am making. Definite length, exact length is an assumption that I am making because that appeals to me.
So I was having only one question, which is related to this Vedic and the astrology prediction nowadays people are doing based on the example which I am facing in my personal life, like if I get a match kind of thing. So people generally use apps kind of thing, and they will give some prediction based on the points, and they will decide the life kind of. So what kind of mathematics behind this logic basically?
I think that this Vedic mathematics is a bunkum, really. I got into trouble saying that. I mean, that's just that's a revivalist thing. I mean, manufactured thing. I mean, there's nothing there. I do not know. I mean, only dangerous thing that's happening, actually, that's what happened in the ICME conference this time, was that this gentleman who actually came to talk about Vedic mathematics began with ancient Indian mathematics, and he put all of that and this 20th century product called Vedic mathematics and packaged them all, calling all of them together as Vedic mathematics, which is absolutely a mischievous thing, because ancient Indian mathematical knowledge does not have contribution only from Vedic scholars, and not even all of them actually were kind of, they believed in God or something like that. Not all of them. Aryabhatta perhaps was not. That's what Professor Kannan, who is also my teacher, says that, And there were also contributions from Buddhist traditions, Jain traditions. The mathematics was written also in Prakrit language. So, all that. And then later Islamic contribution, all of that is our inheritance. So, when we talk about ancient Indian mathematics, we skip all of that. We just only talk about, if you want to package everything as Vedic mathematics, then you are doing some mischief there. And that's a very dangerous kind of mischief. And, when we are living in a country when we are actually asking questions about, challenging caste or things like that, I mean, it's not going to, if you are imposing mathematics as Vedic mathematics on me, I am going to develop an allergy to it, because Vedic knowledge, Vedic forms could have been, I may see them as oppressive, as excluding. So it's actually very problematic.
In these days of artificial intelligence, how do you get the students get interested in maths or improve their mathematical proficiency? Because from what I read, in Western countries, they have observed a decline in the IQ over the past 50 years, and I'm sure it's happening in India. And Indian students generally are not doing well in maths tests, in international maths tests. We are no longer participating in some of them. How do you improve the
Before you answer, I think I'll answer his question. This question can be answered by ChatGPT.
My question was on a comment that you made on D'Ambrio's research, where he says that the motivation for ethnomathematics can go beyond the mere utilitarian. So bringing that down to the Indian context, the Bhatta-Bhaskara system and also the Madhava system, I'm not sure if he's given official credit for the development of the infinite series, I think a century before Newton and Leibniz. Never mind that. I'm not going in that direction. I just want to clarify that. But when you studied the Bhatta-Bhaskara system, Madhava system of Indian mathematics, what were your personal learnings? What were your thoughts about what motivated them, the cultural context in which they developed this mathematics? Thank you.
Okay. See, that Sendil Babu uses to say that when we are talking about Indian mathematics and Indian mathematics and Indian mathematics and the greatness of Indian mathematics and the things that we did before others did, we do not refer to a whole lot of other forms of mathematical knowledge that exists with the people. That is also mathematical knowledge. And so he says that he is not talking about the traditional form of Sanskritic knowledge that one is talking about as owning it as Indian mathematics. He is saying that I'm talking about something else. That is why he calls this Bhatta-Bhaskara tradition, just for want of a proper name. That's all. I'm simply quoting him. Okay. And for me, the motivation actually comes from like this. See, one is that every discipline has been critiqued actually. I really asked myself this question now. I'm asking, like, why did I not ask when I was a student of mathematics? Why did I not ask why mathematics should be axiomatic? I never asked that question. Took it for granted. It seemed like that's the right way to do mathematics. How? Why? Never asked this question. Nobody ever asked. And as a feminist, as someone who read also a good bit of feminist critique of science, it wasn't so very easy to critique mathematics. It seemed like mathematics was already clear. There is one mathematics and this is the right way to do mathematics, and it seemed like there's no question about it. Now actually education allows us to question mathematics critically. So ethnomathematics, this whole thing actually allows me to say that this is only one way to do mathematics. And I need not necessarily have it all the time. Maybe one day this will go. This mathematics may not exist forever. I can create another form of mathematical knowledge. Maybe some community can challenge and come up with new forms of mathematical knowledge maybe. That I can still exist as a respectable human being with sufficient intelligence, even though I may not really be able to, do some of those things that you are teaching me in school in mathematics. that I may have other forms of, this is something, and like I said, no, that so many school children actually, you know, we have this ASER data coming out every year, that 8th grade children cannot do third class mathematics, etc. This kind of data every year they are submitting it, and it's our practical knowledge also. You go and ask, test children, they are not able to multiply, they are not able to, but what we do not actually check is the kind of oral mathematical knowledge that they may have. They will have, I am not saying they may have.
Well, Alex Adventures in Numberland, you must have come across.
Okay.
So it tells you a lot about, you know, numbers and cultures in a storytelling manner. So my question is, when the perception of numbers and quantities that we are talking about, not the reality of it, so how do we ensure that there is no cultural appropriation of the numbers? It can also lead to the biases on its own, and there may be some issues with that. So what we are trying to, you know, get rid of, probably we might get involved into it. So your comment on that. No, my whole question is about, when we say the numbers are also culturally contextual, it's a perception that built by the communities and others. So there can also be generalization based on these appropriations by the culture. So does ethnomathematics also look into these aspects?
Area, domain, you know, ethnomathematics is a term actually coined basically to talk about the fact that there are mathematical practices that lie outside what mathematicians refer to as mathematics. But, you know, abstraction, you know, puzzles exist. Puzzles exist. All cultures have puzzles. Once a mathematician, friend of mine, Manikam from Tamil Nadu, he actually gave me a puzzle. When we were traveling somewhere, I was talking about feminism. In order to divert my attention, he gave me a puzzle, very interesting one. He said that mother makes some number of idlis and puts it in a dabba and tells her sons, 3 of them, that, see, listen, I made some idlis, you divide it equally amongst yourselves and eat, and she goes off to work in the field. Now, nobody ever breaks a idli and has only half a idli or something like that. You have one full idli or you don't. So the first one gets up and divides the number of idlis into 3 equal parts, eats his share and mixes up the remaining and goes off. The second one gets up and he does not know that the first one has actually already eaten his share. So he once again divides it into 3 equal parts and he eats his share and mixes up the remaining and goes off. Then the third one does the same. Then when the mother comes back, she finds that there are still some idlis left. She again divides it into 3 equal parts and distributes. If that's the case, what is the minimum number of idlis that she would have made? Now the thing is not 0. Of course, 0 is a possible answer. One wants to say what is the non-zero answer to this. Okay, is there an answer here already? Did someone say 9? No, it's not 9. So this question, this puzzle was given, and then later on he told me that he got this puzzle from his grandfather who was a farmer, and it was not dividing into 3. It was in tens, like, you know, huge number. So much was there. He had 10 sons, amongst whom it was divided. The story went like that. So these puzzles, why do people come up with puzzles also? And how do you look at numbers in puzzles? How do we look at numbers, right? Now when we look at numbers also, we begin by teaching children. I mean, school teachers actually say that, you know, in our school we don't give admission to class 1 unless somebody can, somebody knows numbers up to 300. I mean, you are expecting a 5-year-old, 6-year-old to know what is 256. What is 256? It is 2 and 5 and 6? Or is it 256 as a quantity? What does it refer to? How will a child know 256? What does it mean to say that one knows a number? One may know a number in a context. When mathematicians, as students of mathematics, when we look at numbers, we look at it in a certain kind of an abstract. And let me also tell you that if one is obsessed with axiomatization, even numbers are axiomatized. So you have the Peano axioms, which actually axiomatizes the whole of natural numbers, which, you know, because in we use numbers in context. When somebody utters a number, when 256 is uttered, some image comes into your mind. How would you actually work with numbers if you do not know how to write? How do you work with numbers? You have some mental model of it, right? It represents something for you. It's not that abstract number that you deal with. Most of us actually have 256 as 2 and 5 and 6 as a number written. and then we do column operations or whatever that we want with them. But it is something, we don't really deal with what is 256 otherwise. And 256 in the context of counting is one thing. When you are using the number, when you are talking in the context of measurement, it is actually a very fascinating thing to actually ask oneself. When in the measurement context, are you certain that 2 plus 2 is 4? Now, I am saying this also because while browsing the net, I looked at an article which said, okay, we are talking about culturally relevant mathematics and relativism and things like that. So will 2 plus 2 become 5? Now, no ethnomathematician is claiming that 2 plus 2 is 5. Nobody is saying that. But the very question as to 2 plus 2 is equal to 4 does not make sense. It doesn't make sense in itself. It has to be you need to actually do something to make it meaningful. Otherwise, you cannot answer that question. And if you try to answer it in the context of counting, you can actually have the answer that it is 2 plus 2 is 4. When you have 2 apples and 2 more apples, then you get 4 apples. But if you have 2 meters of cloth and 2 more meters of cloth, or you walk 2 kilometers and walk 2 more kilometers, can you actually say for sure that you walked 4 kilometers or somewhere close to 4 kilometers? Measurement context is actually, it's not exact. And therefore, this whole simplifying it as 2 plus 2 is 4, or these things don't work. I do not know whether I actually answered your question, but I think that, maybe I was trying to answer, yeah.
A subject, a discipline, economics, where I have to teach some mathematics, but as you were saying, it's discipline, so it's use-based. So some interesting insights I got from what you were saying, which might appeal in future. And, so the first is basically an insight, and make of it what you will. I have found, I've taught all over the world, Brazil actually, and the UK, India. There is a basic problem I have with well-trained economic students from Oxbridge or Harvard. They cannot distinguish between an estimate, a projection, and a forecast, right? And I found with Indian students that intuitively they get it. So when I say to them, my OECD students faint when I say all GDP numbers are estimates, so please don't ask me whether GDP numbers are miscalculated or low or high. There may be a political agenda, but there is no true GDP. My Indian students get it at once. Then I realized, because when we do recipes in India, we do it through andaza. So the word andaza is very much part of all kinds of Indian scientific discourse. Whereas, with respect to all astrology lovers, projections belong to the realm of astrology and forecast too. But estimates are something we have been doing very well. So that is actually, I often think that when we teach mathematics, when I receive those school students at the junior level, if you're able to build on these strengths and identify them, will be good. Now, second is, this is a question, but I've observed in my career and beyond, and also just normally, I'll give you an example of India or UK where I've lived in a minute. There is coexistence of mathematical forms, including definition and measurement. For example, and aviation is ideal, because aviation is so global. If you go and look at a moving map, you'll get your numbers in both metric and imperial and sometimes, third systems. Similarly, in India, we measure our temperature in Fahrenheit and centigrade, but we measure everything else, many other things metrically. In England, I found it's exactly the opposite. I couldn't buy a centigrade thermometer, so when I had a fever, I had no idea whether I was dying or not, because they use centigrade for that, but they use everything else, they continue to use imperial measurements. This coexistence also exists in economics, and it'd be interesting to get your thoughts on how this sort of coexistence evolves, because then that would mean, for me, question, that ethnic economics, as you're describing, is actually plurality in mathematics. Like you're saying, axioms are bad. So in economics, you can define equilibrium using calculus, and either you teach calculus like I learned it, limits, real analysis, or through matrix algebra. Indians are more comfortable with matrix algebra, so now we are teaching equilibrium using matrix algebra. But the two coexist comfortably, and the student has a choice. If they like real analysis, go there. If you want matrices, go there. So would you say the way forward?
No, but then they are both within the same, actually are doing mathematics, which is again differently, which I don't know.
Yeah.
In which case it will be interesting. Then it becomes an ethnomathematical
It's completely different where we do it, because you're taught, it's protocol, right? So you're taught to do it through real analysis and limits, or you start with determinants, matrices, arrays. And determinants, matrices, arrays, Indian students are more comfortable with. They're more comfortable with limits. So I'm just wondering whether when you say ethnomathematics, are we talking about different systems coexisting, talking to each other, or are we talking about separate evolutionary systems?
They are different in epistemological sense, they are different. they validate knowledge differently. Their expectations about knowledge is different. And in that sense that one is saying that, I mean, it's, that, I mean, we all know that a same theorem may have several different proofs coming from very many different places actually. That does not mean that these are ethnomathematical forms of knowledge. They all actually have the same fundamental belief about mathematics and assumptions about, so they will not be ethnomathematics. So I mean, as economists, how you are using it, I mean, I wouldn't be able to answer it right now from here. I do not know, but it could be also, we do not know. It could be argued also. We do not know how you do mathematics. You don't talk much to mathematicians, right? So then I think there is probably some chance that there is some ethnomathematics there.